Alright, continuing on. So, in this video I hope to do microwave and infrared. And then in the third video, the last three, and then kind of wrapping it up. Microwave's going to take a little while because I have this cool video of demos I want to show you. So yeah, let's start right in with microwaves. Microwaves are the next grouping of photons in the electromagnetic spectrum, shorter wavelengths than radio, higher energy. This is a picture of the cosmic microwave background. I'm going to talk about this in much more detail next quarter when I talk about cosmology. But just to give you a quick idea, this is basically a picture of the entire sky in the microwave background, in the microwave regime. And so you just take a microwave detector, just like a camera on your phone is a visible detector, and actually, if you may not have known this, but it's also a little bit of an infrared detector. And this is what the picture looks like. This darker blue is low intensity, not very bright in the microwave light area, and here these red spots are really bright. But when I talk about this, you're going to find that there's really not much of a difference. It's pretty smooth in general in terms of there's not much of a difference in brightness between the two. It's just exaggerated for the purpose of this picture. So that's cool. And also a picture of the sun in microwave. It's actually frames, looks like every 10 minutes. So it's kind of animated in a sense. And it doesn't seem to be as many features as you saw in the radio version of the sun. You see some brighter spots here and here. Um, this might be just a time of lower activity for the sun. With the radio one, you saw a bunch of spots kind of in these two bands. This again, you might see more if the sun were more active. I don't know, 311. That's today. That's yesterday. Uh, eh, I don't know. I haven't been keeping track of the sun these days, so I don't know how active it is right now. Um, but yeah, this is the sun in microwave very recently. Kind of cool. So this last part I want to show you for microwaves is actually a demo of a microwave oven. So I don't know if you knew this, but your microwave oven uh, gives off two types of light. You have a light bulb in there so you can see your food cook. That's visible light. But there's also microwave light given off, and that's what heats your food up. Literally, let's go back here. They're the same thing, electromagnetic waves. In fact, it's this electric and magnetic part that jiggles your food molecules, which are actually really the water molecules in your food, and that's what heats them up. So that's kind of cool. Before I forget, another thing to notice about microwaves, you can kind of see the microwave here, is on the door you have like a metal mesh screen so that you can see in and see the food cook. If you take a look at your microwave real quick, you'll know what I'm talking about. The wavelength of microwaves are long enough so that they actually can't escape that mesh. Of course, visible light wavelengths are short enough, and they go right through those holes in the mesh, so you can see your food. But that's like a solid wall for microwaves. That's kind of cool. So there's no danger of getting near the microwave, and no microwaves are escaping from that. So, all right. So I guess is it almost a decade ago or so? I took a class for my master's in physics education at University of Virginia, and some of the classes were distant learning classes. So they sent me basically some VHS tapes. That's why the quality of this is kind of crappy because I converted it from VHS. But this is they basically filmed a college lecture, undergraduate physics college lecture, which is pretty cool. And what was great about it is they had lots of demos. And so he's going to do some demos with a microwave, and you can see what microwave electromagnetic radiation, microwave light, can do. Don't try this at home. This is just a laboratory microwave. It's not one that they're going to be cooking in, and so you don't want to do that. So I'm going to play till the end. So it's about 4 or 5-ish minutes, and then I'll talk about infrared, and this video should be good. So enjoy. These are some fun demos.
Oh, that brings us to the question again, and then a bunch of demonstrations. What do you think will happen if you put a CD, which incidentally has a very thin layer of aluminum in it? It will do nothing, burn up the microwave oven, or burn up the CD. How many think 1, it'll do nothing? How many think 2, it'll burn up the microwave oven? How many think 3, it'll burn up the CD? Okay, we've got a majority of people by far voting for burn up the CD. Let's give it a try. Okay, actually, I've got a series of experiments to do here with the microwave oven. The first one to do is the official demonstration. When they service your microwave oven and they want to show you it's still working, they get a tool like this, which consists of some little neon bulbs with pieces of metal projecting into them. Now, if you put this in microwaves, charge will be pushed back and forth in those pieces of metal. And so, once each half cycle, a lot of charge will build up on the point of one of these little wires, and it undergo a corona discharge and jump off into the neon and light the neon up. So if I put this guy in here, yeah, it's awfully high. Need something a little less high. How safe is that? Safe enough. Oh, please stand up here, guy. So I just want to show you that we do have fields in there. There really are electromagnetic fields inside the microwave oven. Okay? They really do push charges back and forth. They light up the neon in the charges. But that's not nearly as fun as putting another device that has metal in it. Let's see, is this one I want to do next? Yeah. So we've got a clear light bulb. It has metal inside it. It has gas inside the bulb. Bulbs do not have a vacuum in them. If I do this right, I want to put a little bit of water in here to absorb some of the microwaves. I've blown up a beaker before. But if I now turn on the microwaves, we'll push charges back and forth through that metal. The metal will get hot, and so we'll probably get incandescent glowing pieces of metal, white hot pieces of metal. But we should also get the gas lighting up. We'll give it a try. It's more fun if you can see it better. Okay? I can't do it too long, because if I do it too long, it really does explode, okay? I know this from really scary experience. Okay. Yeah, it all gets really hot. Okay, so you understand how that happened so far? Now I know I got one that's perfectly safe, but potentially smelly. Have you ever wondered what to do with all the AOL CDs? I collect them faster than I can use them here for this experiment. So here is what you're supposed to do. And it does not injure the microwave oven at all. Okay? So we're about to zap that CD in the microwave. It's got a very thin layer of aluminum in it. The aluminum will have charges driven back and forth through it by the microwave fields. It's so thin that it will heat up as a result of this. And so will the plastic. It turns out that plastic expands with heat faster than aluminum does. So the plastic gets bigger and tears the aluminum into little shreds. And the little shreds have sharp edges. And when you've got little sharp edges and you put charge on them, you get corona discharge. Remember that idea? So we'll get sparks. So here's the story. You're going to see 2 seconds of nothing as the magnetron, the source of microwaves, gets hot. It's another vacuum tube. 2 seconds of sparkland, okay? Or actually 2 seconds of heating and then 2 seconds of sparks everywhere. Ready? You can try this. Those of you who can't see, come up and try it after class. Here you go. Ready? 2 seconds of nothing. 2 seconds of sparkland. And then, well, okay, and I got to stop because otherwise it gets real smelly. Don't cook it more than about 6 seconds. For those of you who missed it. Ready? Okay? Well, still more. Don't leave yet. Next thing to do, what about if you have a burning match in a microwave oven? Once in a while you catch things on fire. If you put a very thin twist tie, for example, on a bag, it will heat up to the point where it will catch fire. What happens once you catch something on fire in a microwave oven? Well, you can actually get, once you get a fire, there are ways in which you can get charged particles into the gas inside the microwave oven. What's known as a plasma. You end up with a gas that has electric charges in it. A charged gas can absorb microwaves directly and be heated directly by the microwaves and form, in this case, balls of white-hot plasma. So that's what we're going to go for. I will do it once. I'm going to do it once just with a match open by itself, and then we'll do one with a little cone in there. Oops, don't go out on me. Ah. There's too much wind. Wait a second. I got to take the cover off the microwave oven to get rid of the wind. All right. Now I got putty all over my fingers. It's really gooey. Time pressure is terrible. Okay, come on, guy. We can still do better. Now, I put the cone in here. Let's get this working right. You haven't seen the plasma balls yet. This is just the boring stuff. It may be fun to you, but it's like... See the plasma ball up there? I think that's enough. All right. Excuse me?
All right. So that was cool. A lot of cool demos, and shows you the effect that microwave light can have on things. So we're at 13 minutes. That took a long time just for microwaves. I think maybe, because I got a few videos for infrared. Actually, I think I'm just going to stop it short here, and maybe try to finish up everything in the third video with infrared in it. So yeah, I'll stop here.